Hey everyone, and welcome to This Explainer. I am so thrilled you're here today. We are jumping right into an absolute cornerstone of algebra, writing linear equations, and more specifically, we're going to decode the mysteries of parallel and perpendicular lines. Okay, let's dive right in, because by the time we're done here, you won't just be memorizing a bunch of random formulas. No way. You are going to truly understand the precise geometric architecture behind exactly how lines interact on a coordinate plane. So here is our roadmap for today. First, writing equations from points. Second, parallel and perpendicular slopes. Third, vertical and horizontal exceptions. Fourth, a coordinate example and verification. Fifth, we'll do some checks for understanding. And finally, number 6, a quick recap and transfer. All right, let's kick things off with section 1, writing equations from points. Now, before we can go comparing different lines to one another, we really need to know how to build a single line from scratch, using nothing but a coordinate point and a rate of change. We're literally building the foundation of linear equations here. To construct our equation, we follow a pretty logical progression. If you're given one point and a slope, you start with point-slope reasoning. This lets you anchor your line to that specific coordinate and just map out the rate of change from there. But, we don't usually stop there. Step 2 is to isolate y. We rearrange the equation into slope-intercept form, which is y equals mx plus b. Why do we do this? Because slope-intercept form is absolutely the best format for graphing. It's so clean. Now, you might be wondering, what if you're only given 2 points? Super easy. Step 3 tells us to just calculate the slope between those 2 points first, using our trusty slope formula. And then, just repeat steps 1 and 2. You've got this. Moving right along, section 2, parallel and perpendicular slopes. Okay, so now that we can write an equation for a single line, what happens when we throw 2 lines onto the exact same coordinate plane? Well, this perfectly illustrates the 2 main rules we really need to know. First up, parallel lines. These are distinct, non-vertical lines that will never, ever intersect. Like they will go on to infinity without touching. Why? Because they share the exact same slope. Their rate of change is absolutely identical. Perpendicular lines, on the flip side, intersect at a perfect, crisp 90-degree angle. But for this to happen, their slopes have to be negative reciprocals of each other. So let's say one line has a slope of positive 2/3. A perpendicular line must have a slope of negative 3/2. You just flip the fraction and you flip the sign. Now I want to pose a question to you right now, because this is a very common trap that students fall into all the time. If you have an equation and you leave the slope completely alone, but you change the y-intercept, does that make the new line perpendicular to the original? Take a quick second to think about that. So here is the crucial takeaway. Changing the y-intercept does absolutely nothing to the angle of the line. Nothing at all. Changing the b in y equals mx plus b simply shifts the entire line straight up or down the y-axis. Because the slope m remains exactly the same, you're literally just creating a parallel line. Never a perpendicular one. To get a perpendicular line, the slope itself fundamentally has to change to that negative reciprocal we just talked about. All right, section 3, vertical and horizontal exceptions. You might have actually noticed that I kept using the word non-vertical when I was defining those rules a minute ago. Well, that brings us to a couple of edge cases that kind of require their own special logic. Let's look at how we handle the extremes. A horizontal line is perfectly flat, meaning it has a slope of exactly 0. Think of walking on totally flat ground. Its equation is simply y equals whatever the y-intercept is, or y equals b. A vertical line, however, goes straight up and down. Its slope is undefined. Why? Because you literally cannot divide by 0. Therefore, its equation is x equals a, where a is the x-intercept. By isolating vertical and horizontal lines like this, we completely prevent their strange slopes from confusing our primary rules for standard slanted lines. Oh, and bonus fact, a horizontal line is always perpendicular to a vertical line and vice versa. Let's see this in action. Section 4, coordinate example and verification. Let's put all this theory into some actual practice. And I really want to stress something highly important here. We aren't just going to solve this problem, we are going to mathematically prove that our solution is bulletproof. Let's step through this scenario. We need to find a line parallel to y equals 2x plus 1, passing through the coordinate 3, 4. Okay, since it's parallel, we know for a fact it shares the same slope as the original line. The original slope is 2. So our new slope is also 2. Easy enough, right? Now, we use point-slope reasoning with our coordinate 3, 4. We write y minus 4 equals 2 times the quantity x minus 3. To get this into our preferred slope-intercept form, we just distribute that 2, which gives us 2x minus 6, and then add 4 to both sides. Our final beautiful derived equation is y equals 2x minus 2.
But hold on, how do we know we didn't just make some silly arithmetic mistake? We verify. Seriously, this is a vital mathematical habit to get into. We take our derived equation, y equals 2x minus 2, and we plug our given coordinate, 3, 4, right back in for x and y. So, does 4 equal 2 times 3 minus 2? Well, 2 times 3 is 6, and 6 minus 2 is indeed 4. 4 equals 4. The point satisfies the equation perfectly. We just proved without a doubt that our new parallel line actually passes exactly through that required coordinate.
Okay, section 5. Checks for understanding. Time to test your skills. All right, it is your turn. I want you to actively test the knowledge you've just built. Here is your first active recall check. What is the equation of a line perpendicular to y equals negative 1/3 x plus 5 that passes through the point 0, 2? Think about that perpendicular slope rule we talked about and look really closely at that coordinate. All right, let's map out the reasoning together and see how you did. First, we identify the original slope, which is negative 1/3. Because we want a perpendicular line, we desperately need the negative reciprocal. Flip the fraction, flip the sign, and bam, our new slope is a positive 3. Now we need it to pass through 0, 2. You totally could use point slope form here, but if you look closely, an x value of 0 means this coordinate actually is our y-intercept, so b is simply 2. Dropping our slope and y-intercept straight into our formula, our final equation is y equals 3x plus 2. Huge, great job to you if you caught that sneaky y-intercept shortcut. Let's try just one more. Check 2. Write the equation of a line parallel to the horizontal line y equals 4 that passes through the point 2, 7. This one is specifically testing your grasp of those edge case exceptions we covered earlier. So here's the reasoning for this one. The very first step is to recognize that y equals 4 is a horizontal line with a slope of 0. Therefore, logically, any line parallel to it must also be a horizontal line, which means it'll be formatted simply as y equals b. We're given the point 2, 7. Since all y values on a horizontal line are totally identical across the entire line, we just look at the y-coordinate of our point, which is 7. So our final equation is simply y equals 7. See? Relying on those structural rules makes finding the answer remarkably simple. And that brings us to section 6, recap and transfer. We have covered a lot of fantastic ground today, so let's rapidly review our core takeaways just to cement this knowledge in your brain. First, build equations by moving logically from point-slope reasoning right into a clean slope-intercept format. Second, parallel non-vertical lines always share the exact same slope. Third, perpendicular non-vertical lines have slopes that are negative reciprocals of one another. Remember that horizontal and vertical lines act as those special structural exceptions to standard rules. And lastly, and honestly perhaps most importantly, always verify your derived equation by plugging a known coordinate point back in to check your work. It is a lifesaver. To wrap things up, I want to leave you with this somewhat provocative thought. How could you program a computer to draw a perfectly perpendicular cross street on a digital map app like Google Maps or Apple Maps? Think about it. The computer doesn't have eyes. It only understands pure data. By feeding it the algebraic equation of the main road, the computer can instantly calculate the negative reciprocal slope and accurately plot a flawless 90-degree intersection using the exact algebraic rules we just learned today. Mathematics is literally the hidden code that builds our modern world. How cool is that? Keep practicing, definitely keep verifying your answers, and I will see you in the next explainer.